Alright, so welcome guys to this new chapter, dimension reduction. So if you recall from what we're doing previously, we mentioned some of these things, like and I think it was the first chapter itself, where we talked about dimension reduction. That we'll be doing things where you reduce dimensions from a high dimensional space to a low dimensional space. This is because sometimes machine learning models, they face one challenge, and they face many challenges, but one of them was the case of dimensionality. If you remember, case of dimensionality. Sorry, I don't know what's going on with my pen now. Okay, case of dimensionality. This is a case where your number of variables in a data set is sometimes way more than your number of observations. So if n is your number of observations and p is your number of variables, the case of dimensionality happens when n is much less than your p. When n is much less than your p, you have the case of dimensionality. So with dimension reduction techniques, you are able to deal with this problem. So let's see, in this chapter we are learning methods of how to deal with this problem. So let's see what so let me just explain like the process that we have here. So here, let's say we have a big P. That is our original data set. So this is the original data set. Those are the number of the dimensions in the original data set. What you do is you pipe it into a dimension reduction algorithm here. Dimension reduction algorithm. And when it gets into the dimension reduction algorithm, we're going to maybe end up with k dimensions. K dimensions where k is less than p. Then we know we have reduced the dimensions. So that's what we'll be doing in this course here. Not in this course, but in this chapter here. And we know that dimension reduction is composed of linear projection algorithms and manifold algorithms, or manifold learning. So with linear projection, this is when we linearly project data from a high dimensional space to a low dimensional space. And it includes techniques such as your PCA, principal component analysis, singular value decomposition, and random projection. For manifold learning, what we're trying to do is this is also called nonlinear dimension reduction, right? And what we're trying to do is we're looking at, let's say, isomap. Isomap learns the curved distance between 2 points. It uses the curved distance between 2 points rather than the Euclidean distance that we will use in some linear ones. And other techniques like multi-dimensional scaling, which is called MDS, multi-dimensional scaling. We spoke about t-SNE. I call it t-SNE. I don't know what it should be called, but I just call it t-SNE. We spoke about dictionary learning. We talked about independent component analysis, I think, if I remember well. We talked about independent component analysis. So those are some of the discussions that we are going to have in this chapter. But the most important part that we need to emphasize is once data is now in low dimension, we can either use it as is. You can use it as is, right? So that is the use of dimensional reduction. We can reduce the dimensions and use it as is. So which means the dimension reduction was actually the end goal. So if the dimension reduction was the end goal, and then we use it as is. This is usually used in things like anomaly detection, and that will be the next chapter. Anomaly detection. We are going to build an anomaly detection system. Remember, in the previous chapter, we built a sort of a fraud system using supervised learning algorithms. But in the next chapter, we will be building a fraud detection system using the same dataset, but doing anomaly detection via what? by doing dimension reduction. Or once you reduce the dimensions, you can pipe the results into another ML algorithm. This is when, let's say, you want to use a supervised machine learning model at the end. You can do dimension reduction. When you do dimension reduction, you then, after the results are attained, you then pipe it into a supervised machine learning model. Which means dimension reduction in this case is just a process along the way. It's not the end goal. It's a process along the way, right? What is very important is when we are doing, another important point is when we are doing dimension reduction, as we move from high dimensions to low dimensions, we are losing noise. That's the intention. We want to get rid of as much noise as we can, so that we keep the salient information in the dimensions that we will end up with. So we want to keep the salient information. It has to be maintained, but at the same time lose the noise that is there in the data set. That is very, very, very important. When it gets here, the noise would have been reduced, and if we are using an ML algorithm after that, it will behave much better than if we had applied the ML algorithm here, because of the noise that is still there. Dimension reduction reduces the noise, and when we apply that same ML algorithm down here, it might perform actually much, much better. So that is the high level of dimension analysis. In the next video, what we are going to look at, we're going to look at the dataset that we will be using. What dataset are we going to be using to investigate this? It's going to come in the next video, and after that we'll get into the algorithms. So stay tuned for the next video.